So now we're going to talk about some of the ways that we can make errors in the hypothesis testing framework. So first, a couple of things that I want you to think about anytime you're setting up a hypothesis test, because the outcome of your test can be affected by a lot of factors that you want to really consider. The first is the hypotheses that you choose, right? So are these the correct hypotheses for the question you're trying to answer? Did you choose the right test statistic? Is this actually measuring the difference you're trying to measure? If you are simulating your null distribution, the empirical distribution of your statistic under the null, then you need to make sure you're doing a large enough number of simulations so that the empirical distribution is approximately equal to the true theoretical distribution. The data you collected can also affect your results, and this was why we spent some time really going into sampling and sampling techniques and sampling bias, because if you don't have good data, then you're not going to have valid results from these types of tests. And as we saw in the last video, a larger sample is going to lead you to reject the null more reliably if the alternative is in fact true, i.e. you'll have higher statistical power with a larger sample. And then the truth also is important. So is the alternative hypothesis true or is the null true? And if the alternative hypothesis is true, how extreme is the difference? That's the effect size. If the truth is really similar to the null, if you have a small effect size, for example, if your null is that it's a fair coin, but in reality it's biased 49% heads, then even a large sample may not provide enough evidence to reject the null. So these are all important things to consider as you're setting up your hypothesis tests and making your conclusions. And then, even given all of this, let's say you did all of it the best you could your conclusion still be wrong? And the answer, unfortunately, is yes. And there's two main ways we're wrong in these tests. The first is, given that the null is true, your test rejects it. Okay, so these boxes I have here are actually, from a probability standpoint, really representing a probability that you incorrectly reject. So this is reject given the null is true. So there is some probability that that will happen. That's conditional. There's also a conditional probability that when the null is false, you fail to realize it, right? Fail to reject. So these are two conditional probabilities that can happen, and we're trying to set up our test to minimize those conditional probabilities. So the first one, let me erase this so you can see the little picture, is typically called a type 1 error, or sometimes a false positive, right? But again, the null is true and you reject it. And the second one, let me go back. And how do we control that type of error? Well, that's where you can directly control that with your significance level that you choose, because that probability is exactly equal to your significance level. So you basically decide your tolerance for that type of error and set that equal to your significance or your p-value cutoff. The second type of error, often called type 2 error or false negative, right? This one up here. In order to control that, it turns out, well, that one is exactly equal to 1 minus your power. So the higher your power, the lower your chance of this type of error, because this right here is actually the power of your hypothesis test. The probability that you correctly reject the null given that the null is actually false. So let's look at that first error, that type 1 error. If you recall, right, that significance level really is your error probability. So that's how you can control that, is you basically choose your tolerance level here. But let's think about how that can get compounded when you're doing multiple hypothesis tests. So here's an example. Suppose you do 20 different hypothesis tests, testing the relationship between jelly beans and acne. Okay, spoiler alert, there's no relationship between jelly beans and acne. And let's say that's your null hypothesis, that there's no relationship. Let's assume you conduct each test at a significance level of 5%. If in reality jelly beans aren't actually linked with acne, what's the probability that none of our tests are significant, i.e. that all of our tests correctly fail to reject the null? Take a minute and see if you can figure this out. You can put it on pause. Okay, so I want the probability that none of our tests are significant. Let's look at this. Let's look at the probability none of our tests are significant. Well, that means there's a 95% chance that one of them is not significant, that it's correct, right? And I want all 20 of them to do that. So I have 95% to the 20th to give me the probability that none of our tests are significant. But that's crazy low to think about, because that means that about 1 minus that, about 64% of the time, one or more of these tests will be significant just by chance, even though jelly beans have no effect on acne. So this is how you can see these hypothesis test errors really start to compound anytime you start doing multiple hypothesis tests. And this is actually a real problem. There's a whole term for this. P-hacking is what we call it, when researchers will collect or select data or statistical analysis until non-significant results become significant. Basically, if you just do enough hypothesis tests, eventually by chance, you'll get some that are significant. And so if you hack your data that way, it's not reliable, it's not accurate, and it's an example of what we call p-hacking. So beware of this when you're reading results and or when you're looking at your own results. Now let's revisit the other way the conclusion can be wrong. So when we looked at our type 2 error, in order to control this one, we just make sure your test has large enough power. And so that's what we talked about in the last video, is some of the knobs we can play with to control our power. Now I'm going to provide another bit of a contrast or caveat in interpreting your hypothesis test results, because you can get statistically significant results, right? So maybe your test rejects the null. You have a significance cutoff of 5%. So you can say, I reject the null and this is statistically significant. That doesn't give us any insight as to the actual magnitude of the effect size, right? It's quite possible that you rejected the null, that the coin was fair, and in reality, the actual effect size is that it's, biased towards heads. Maybe the probability of heads is 50.000005, right? Maybe it's just slightly biased. So maybe the effect size, even though statistically we found it to be significant, maybe the effect size is meaningless. Maybe it's not really useful in practical use, right? So a statistical test can't tell you whether the actual effect size is large enough to be important in your field. And you can estimate the effect size by seeing the effect size you get from your sample, right? So what is the difference between, or basically what's your test statistic, your observed test statistic? How far is that from your null? And that gives you an estimate of the actual effect size. And so this is also leading us to the idea that not all statistically significant differences are interesting, right? If you get a large enough sample size, you're going to increase your statistical power to detect small effects. And so if you turn up that knob large enough, you basically can start to detect an effect that's so minuscule that it's not really meaningful in practice. And the other way that small effect sizes can still produce what seems to be statistically significant is if you have very low sample variability. When that's the case, your hypothesis test can produce more precise estimates of the population's effect, and then this will allow the test to detect tiny effects. So that may sound great. It depends what you're trying to detect, right? But this is really leading us to needing an additional method, right? In addition to these hypothesis tests, we need a method to determine whether the estimated effect is still practically significant when we factor in the margin of error from sampling. And that's really what we are able to capture with the idea of confidence intervals, which is the topic of our next set of videos.